You know, in the world of high-performance systems, there's this unsung hero that works behind the scenes, making everything feel incredibly fast and responsive. Today, we're going to pull back the curtain on that secret weapon, caching. I mean, really think about it. You tap a button, and boom, the content is just there. There's no waiting, no annoying loading spinners. How on earth do they pull that off, especially with millions of us hitting their servers all at the same time? Well, the performance difference can be absolutely massive. We're talking up to 50 times faster to read data from a cache compared to a regular database. And that right there is the difference between a user who stays happy and engaged and one who just leaves. So what is this magic trick? It all boils down to one single powerful idea that turns systems from snails into rocket ships. And that idea, of course, is caching. So let's break down exactly how it works. Okay, so why do we even need this in the first place? Well, the story really starts with the database. Databases are fantastic at what they do, storing our data safely on a disk. But that very act, going to a physical disk, is precisely what makes them slow. And just look at the raw numbers here. It's night and day. A database read on the left might take around 50 milliseconds. That's because it has to go find the data on a physical, maybe even spinning disk. But a cache read, just 1 millisecond. Why? Because the cache holds that data in super fast memory, which is right there next to the computer's brain, completely avoiding that slow trip to the disk. This is the fundamental speed boost we are all chasing. Right, so caching isn't just one single thing you plug in. It's more of a strategy that you can apply at different layers all across your system. Think of these as different tools in an engineer's toolkit, with each one being perfect for a specific job. Now, this is the big one, the one most people think of. It's a separate service, something like Redis or Memcached, that sits right between your application and your database. And because it's a shared service, all of your application servers can talk to it, which is an absolute lifesaver for scaling up. For any high-traffic system, this is pretty much the default starting point. The next tool in our kit solves a totally different problem. Not just slow disks, but the speed of light itself, or, just physical distance. A CDN is a massive global network of servers that stores copies of your content, things like images and videos, geographically close to your users. This means they can download that content from a server that's practically in their backyard instead of one halfway across the planet. And this visual just makes the impact crystal clear. Without a CDN, like you see on the left, a request from someone in India to a server in, say, Virginia could take a sluggish 300 milliseconds. But with a CDN, that same request hits a local server right there in India and gets served in just 20 milliseconds. That is a huge, massive improvement that your users will definitely feel. Now we're getting even closer to the user. In fact, we're right on their own device. The browser cache is the perfect example of this. By storing data locally on your phone or computer, you can sometimes skip the network call completely, making things feel truly instantaneous. But, and there's always a but, right? The big trade-off is that it can be really tricky to make sure that local data doesn't get old and stale. And finally, we have the fastest cache of them all, living right inside the application's own memory. This is perfect for small bits of data that are used all the time but rarely ever change, like feature flags or configuration settings. It is blazing fast. The catch is that it isn't shared between your different servers, so it's more of a specialized tool for a very specific job. Okay, so we know where we can put a cache. Now let's shift gears and talk about how the application, the cache, and the database all talk to each other. These are the core patterns, the architectures that govern how all the data flows. So let's walk through the most common pattern by far, which is called cache aside. Here's how it works. First, the app looks in the cache. If the data is there, we call that a cache hit. It just returns it. Easy. If it's not there, a cache miss, the app then goes to the database, grabs the data, stores a copy in the cache for next time, and then returns it. It's called lazy loading because you only bother caching something when it's actually requested. And this is so important. If you only remember one pattern from this whole thing, make it this one. Cache aside is the workhorse. It's the default. If you're ever in a system design interview, this is your starting point. And why? Well, because it's simple, it's incredibly effective, and it keeps your cache from getting clogged up with a bunch of data that nobody ever actually looks at. Now, there are other patterns, of course. You've got write-through, which really prioritizes data consistency by writing to the cache and the database at the same time, but that makes your writes a bit slower. Then there's write behind, which makes writes feel super fast because it only writes to the cache first and deals with the database later. The risk there? You might lose data if the cache crashes before it saves. It's always about trade-offs. Okay, so it all sounds amazing, right? Just add a cache and everything gets faster. Well, not so fast. For all of its incredible benefits, caching brings its own set of really complex problems. Adding a cache isn't a silver bullet, it's a trade-off. You're trading future complexity for speed right now. And that brings us to one of the most classic, most dangerous failure modes in any cached system. It even has a cool, dramatic name: the thundering herd. So imagine a really popular piece of content, maybe the homepage of a news site. Its cache entry expires. In that single instant, thousands, maybe tens of thousands of users all requested at the exact same moment. They all miss the cache, and they all slam the database simultaneously. This sudden spike, this thundering herd of requests can easily crush your database and cause the whole system to fail. And there are other dangers too. You have cache consistency. That's the classic problem where you update your profile picture, but all your friends still see the old one for a few minutes. Super annoying. Then you've got hotkeys. This is where a single piece of data, maybe a viral video, becomes so popular that the one cache server holding it just gets overwhelmed by all the traffic, creating a new bottleneck. So with all these options and all these potential dangers, how do you actually put this all together? Well, engineers don't just add caches randomly and hope for the best. They follow a very deliberate, systematic process to make sure it actually solves the right problem without creating new ones. And here's that playbook. It's basically 5 steps. First, and this is non-negotiable, you identify the real bottleneck. Second, you decide what to cache. You want to focus on data that's read a lot but doesn't change very often. Third, you choose your architecture, and you'll probably start with cache aside. Fourth, you need a plan to kick old data out, an eviction policy. And finally, and this is so important, you have to plan for failure and address all those downsides we just talked about. So let's boil this all down. What are the core takeaways? Number 1, caching is always a trade of complexity for speed. Number 2, use it like a scalpel to solve specific bottlenecks, not like a hammer. 3, you absolutely must understand the failure modes like stampedes and stale data. 4, always start with the cache side pattern. And maybe the most important rule of all, don't cache everything. Be strategic. And really, that gets to the heart of what system design is all about. You solve one problem, and in doing so, you often create new, different challenges. Caching fixes the slow database, but now you have to worry about cache stampedes and data consistency. It really makes you wonder, once your reads are lightning fast, what's the very next bottleneck you'd go after in your system?